So before we go over what we did last time, let's consider why are we doing it. So the idea is, if you have a chemical reaction, A plus B going to C plus D, and you want to study whether this reaction is going to go in the forward direction, that is given A and B, will you form the product C and D? Or is it going to go in the backward direction? Given C and D, you're going to form A and B or something else. So if the entropy of C plus D, and let's say this reaction is happening in a thermally insulated system, right? There is no contact with the rest of the universe. So this is our total system, A plus B and C plus D happening together. So if the entropy of C and D, and this is happening at some pressure P and some temperature T. So we can talk about entropy, right? It is a state function at that temperature and pressure. So if the entropy of C plus D is more than A plus B, then what can we say? What will be the preferred direction of the reaction? A plus B going, will it be, you have three options. You have forward, which is A plus B going to C plus D. You have backward, which is C plus D going to A plus B. And you have a third one, which is equilibrium, which is both of them exist under some proportion. Both of them can coexist. So in this first case, what is the preferred direction? Go ahead. Why? Yes, so we know that forward, because delta S, what do we know is the direction for forward change? It is when delta S total increases. And in this case, what is delta S total? Delta S total is indeed SC plus SD minus SA minus SB. And there is nothing else. If this reaction was happening outside in contact with the universe, then it would be more problematic. When SC plus SD is less than SA plus SB, then, so in this case, it is forward. In this case, it is backward, right? So case 1, case 2, and case 3 is when SA plus SB is equal to SC plus SD. In this case, what can we say? Both will exist probably in equal proportion, right? Later on, when we, well, starting today or maybe Monday, we will start talking about free energies, and eventually it is this concept that leads to the concept of chemical equilibrium. Given what is the difference of their entropies, we can decide, we can discuss whether the reaction will, you will have 20% AB and 75% C plus D. What are the proportions of things that you're going to find are essentially just given by entropies. Bit more complicated than just entropies, because this reaction was happening in completely insulated. That's not going to happen most of the time. We will have to consider the surroundings also. So this is the key idea. So just to recap it, if delta S total is more than 0, then forward direction is spontaneous. And here delta S total is defined as S forward, S product minus S reactant. If delta S total is negative, then backward is spontaneous. If delta S total is 0, then it's a reversible reaction, and reversibility basically leads to the state of equilibrium. And once we finish our free energies, we will start talking about equilibrium quite a lot, which is really, all of this is machinery to get to start talking about equilibrium. None of this is telling us how much time will it take to get to equilibrium. That is not answered by thermodynamics. That is the subject of kinetics. So with this preamble, let's look at what we were doing last time, which is we were looking at a gas expanding and calculating the entropy change of the gas and entropy change of the surroundings, okay? So let's do that. Let's draw a line in the middle, because we are going to be looking at two scenarios which are very similar apart from a slight change, okay? So we have case 1 over here, and we have case 2 over here. In both cases, we have a container which is full of, which has some gas particles inside it, okay? And what is happening is that initially these gas particles, they are at a volume VI, and you are letting them expand to some volume VF. Over here also they are at VI, and then they are expanding to some VF, okay? There is, so far it's both the same. There is, and another similarity in both of them is they are isothermal expansion. And notice we are not talking about reversibility because we are trying to calculate whether it will be reversible or not by calculating delta S total. This is also isothermal expansion. The difference now is this one, as it expands, it's expanding against an atmosphere which is also made up of lots of gas molecules, right? So that's what I'm trying to draw outside. You have this atmosphere or surroundings, and the expansion is happening against this surrounding. So as you are, and for both of them, you are physically, what you're doing is to give some heat to the system, okay? You're heating it. This is in a test tube and you're heating it from the bottom and it's expanding. In the first case, it is expanding against the surroundings. It is doing some work against the surrounding. In the second case, it is out in way beyond the reaches of the solar system, or somewhere in the solar system where there is basically vacuum. Okay, there is no surrounding. It's expanding. You went out, you sat on a rocket, you are very rich, you are Elon Musk or whatever, you have money to burn, you sat on a rocket, you went outside, you opened the rocket door, you put a test tube and you started heating the test tube, right? And you're calculating whether this is going to be reversible or not. Because you have so much money, you can do that, right? So that's what it is. So in both cases, we would like to calculate delta S total, which is delta S system plus delta S surrounding, and see whether this thing is positive, negative, or zero. And that will tell us whether it's reversible or not, okay? Let's start piece by piece. Delta S system, will it be same or different for both cases? Given that the temperature and pressure of care, I'm doing it in that upper atmosphere, so you'll be like, oh, temperature and pressure is different, right? But given, let's assume that temperature, pressure, etc. is same. Let's not. So I'm doing a bit of jugglery here. But assuming everything else is same, what will the delta S system be different? The delta S for the gas. Any ideas? Why not? Because it's a state function, right? Once it gets to a certain volume and it equilibrates at that volume, it's going to be the same. So the idea is that delta S system is same for both. So let's calculate delta S system for the first one, and then we can directly use it for the second one. So delta S system over here is going to be integral of delta Q reversible by temperature as you go from VI to VF. Immediately we are faced with a problem. We don't know whether this expansion is reversible or not, right? That's what we are trying to calculate, correct? That's what we are trying to show, that delta S total. Maybe it's zero. If delta S total is zero, then we could have used the heat given to this process. But how do we get Q reversible over here? So in order to do that, and one more assumption which I forget, this is all for a perfect gas. If it was not for perfect gas, the math would be a bit harder. As you saw in problem 1 in the midterm, math gets harder. Otherwise, the concepts are very similar. So this is isothermal expansion of a perfect gas. So we know that irrespective of what delta Q is, whether reversible or irreversible, it is going to follow delta U is equal to delta Q plus delta W. Perfect gas, isothermal expansion. What can we say about delta U? Perfect gas, isothermal expansion, zero. There we go. Maybe you guys have now understood this too well. Normally in the previous classes, when I asked for delta U, isothermal, people say zero anyway, perfect or imperfect. But for perfect, it is zero. Delta Q plus delta W. So therefore, delta Q is equal to minus delta W or delta Q is equal to plus PdV. Okay. And however, strictly speaking, this should be P external, right? Because that is the work done. It's the P external. But over here in this formula, we are going to take it as VIVF P gas dV by T. Why can we do that? We can do that because entropy is a state function. It doesn't matter what path we take, whether the pressure was just yanked up or whether the pressure was in decrease, whether the pressure, in this case, pressure was not yanked up, it's decreased, right? Like we saw in that example that we were talking about, whether it's one step. I'm still thinking about your problem. There is some nuances there, as to why. I will come back to that. But whether the pressure was just decreased or whether it was decreased very gradually, doesn't matter. Entropy is a state function. So we can put P gas over here. And then this becomes P is equal to nRT by V, nRT dV by V, T cancel. And this is a derivation we did in the class like few lectures ago. So this becomes plus nR ln Vf by Vi. Did I get it right? Yeah, I got it right. Plus nR nf, and in this one also, delta S system is going to be the same. It doesn't matter. You have reached the same final condition. Initial, so T and P is same initial and final. That's the point here in both setups. So delta S system is once again plus nR ln Vf by Vi. Now let's think about delta S surrounding. What is delta S surrounding in the second case? Why? Who said 0? Why? There is no surrounding. There is nothing, right? There is nothing. This is just 0. How about this one? Same idea. We have to calculate delta Q surrounding. Let me zoom this up just a bit. Delta Q surrounding reversible by temperature. What can we say about delta Q surrounding? Delta Q surrounding plus delta Q system must be equal to 0, right? If you have a system and the system is taking in some heat, that heat has to be coming from the surrounding. There is nothing except system and surrounding, right? So what I'm going to do is to borrow some space from this other side, because this second part is so easy. So delta S surrounding is therefore minus delta Q reversible system divided by temperature. We just calculated this, right? This is nothing but the minus times the entropy gained by the system. This is minus nR ln Vf by Vi. This thing over here that we just calculated multiplied with a minus sign, because this integral is nothing but the integral over here with a minus sign, right? So what do we get for the total entropy change? 0. What does it say about a gas expanding against an ideal gas expanding against the atmosphere expands reversibly? It could expand, but it could very well contract, and you will probably reach a state of chemical equilibrium. But if the same ideal gas was expanding, so delta S total case 2 is equal to positive, while delta S total case 1 is equal to 0. That's our main idea. If the ideal gas was expanding against the atmosphere, it will be doing it reversibly. If it was expanding against vacuum, it will be doing it irreversibly. What would happen to a van der Waals gas? Would that expansion also be reversible against an atmosphere? Why? You're nodding your head vigorously. Still being kept in by the other gases, and it also has attractive forces itself. Oh, you should try to calculate it. Go ahead. But we can't use delta U is equal to 0 anymore. Delta Q plus delta W is no longer 0 for a van der Waals gas. So you are saying this idea that delta S system is equal to minus delta S surrounding will still apply. It's tricky. Think about it. This could be a good practice problem. Whether van der Waals gas also expands reversibly. Think about a general gas. I mean, think about a real gas. If I filled up some gas in it, is the expansion really reversible? I don't think so. If you put hydrogen in it, it will reach equilibrium though, right? So there is something going on. It will reach equilibrium. You will diffuse it. It looks like it all escaped. But if you had some hydrogen in it and it expanded and it went out into the atmosphere, at the very final end, you will be left with some hydrogen in it. It's just going to be very small amount of hydrogen, right? So it is reversible, but the amount that you have needs to be calculated. So good. Everyone happy with this? Slightly happy, unhappy? Any questions? It's hard to say whether people are happy when they have a mask on, right? Okay. So why are we doing all this? Why did we go through all of this? What we are trying to do with this is to calculate how does entropy change, to really come to terms with calculating the difference in entropy during a process because eventually that tells us whether a process will go in the forward direction or if the process will go in the backward direction or the process will come to equilibrium. When the process comes to equilibrium, law of mass action, which we will look at shortly, allows us to derive how much of the two species will you have in the end. So that's why we are so interested in calculating change in entropy. So that was for a specific case of a perfect gas expanding into the atmosphere or expanding into vacuum. But in general, calculating entropy change. So we know that ds is equal to delta Q reversible by temperature, right? So if I ask you, what is the entropy at a temperature T final, given that you know the entropy at a temperature T initial, you can integrate this equation going from T initial to T final and calculate it. You will have to set up a reversible path. Any reversible path will do, and then you can calculate the entropy. If reversible path was constant pressure, can we simplify equation 1? We can write it now in terms of the heat capacity, right? Because delta Q reversible at constant pressure is Cp dt. This automatically becomes very useful. Hopefully you can see if I'm asking you whether a reaction A plus B is going to C plus D at temperature Ti, and then I make you calculate this. I make you calculate the entropy of everything at temperature Ti. And then I ask you, well, what happens to this reaction at some other temperature, Tf? All you need to know is the heat capacity for every component, A, B, C, D. If you knew Cp for A, B, C, D, delta S total at temperature Ti directly gives delta S total at temperature Tf by looking up the values of Cp. And Cp is something that is easily available in tables. For most materials, Cp has been calculated by doing experiments. In fact, Cp for most molecules and materials was calculated way before 20th century. This was very easy to do, right? People just, that was probably, many PhD theses were written on calculating the Cp of oxygen. And that was one 6-year PhD thesis, right? That was the kind of research that was happening 200 years ago in chemistry because we didn't know very much more. So Cp values are well known and they become immediately useful because we can now calculate whether a reaction is spontaneous at one temperature and use it to judge whether it will be spontaneous at other temperature. This is fine, except when you have a phase change going on. If while going from Ti to Tf, Your liquid changed, your solid changed into liquid, or your liquid changed into gas, or for the material scientists here, your iron changed from alpha to beta, something like that, then you have a problem. This simple formula won't work, and you will have to add one more correction. So this formula 2 needs to be supplemented if phase change happens between Ti and Tf. So what do I mean by that? Let's say we had a solid which is changing to a liquid, which is then changing to a gas, okay, the same species A. And this change happens at Tf. In this case, Tf is T fusion, the fusion temperature. And the second one happens at Tb, which is boiling temperature. And now if I ask you, what is the, if I told you the entropy of A at a temperature Ti, and I, let's give it numbers over here. If I give you the temperature of A, actually even better, let's say I have given you the entropy of A at 0 Kelvin, okay? And you know the heat capacity for all of this. You know the heat capacity for A in its solid form, and its liquid form, and its gas form. And I ask you to calculate the entropy of gas at some temperature T. So I want SA at temperature T from SA at 0 Kelvin. How do I do that? If I was to use formula 2, then it would have been very simple, right? I would just say S is equal to S of 0 plus integral Cp dt by T going from 0 to some temperature T. And I would use different values of Cp when it was, until the temperature it was solid, I will use the Cp for solid. When it was liquid, I would use the Cp of liquid. When it was gas, I would use the Cp of gas, right? So I would write this down. So the question for you is, and here, this is where this is going to be given out, so pay attention. Is this correct to say that SA at temperature T is equal to SA0 plus 0 to 2 TF Cp solid dt by T plus TF by till TB Cp liquid by T dt plus TB till T Cp gas by T dt. Is this correct, or did we miss anything? All right. Okay, why will the entropy change when you're going through the phase changes? Yeah, so the heat capacity, you don't get an ice cream quite yet. There is a second question coming. It's a two-part thing. It's a scam. So I'll just go and eat it myself. No, just kidding. You're correct. So what he's saying is that when you're, what's your name, by the way? Ryan, yeah. Ryan Kim. Yeah. So as you, what is heat capacity? As you give heat to something, the molecules start to move more and more and more, right? And as they move more and more, as the temperature increases, that's the heat capacity. And solids, the way they react to heat is different from the way gases react to heat, right? For a solid, if you give it a lot of heat, it's still stuck in a spot, right? It's not going to, it's like all of you sitting in your chairs nicely. You might jiggle a little bit, but it's not going to be too much. Liquid, you can move around the moon. Gas, you can move around lots and lots. So clearly, Cp is different for solid, liquid, and gas. But there is something else that happens right at the melting temperature or right at the boiling temperature. That is the process of fusion or the process of vaporization, which is known as the latent heat, right? There is some extra heat that goes on into this, that is given into the system. So this is not correct. And this needs to be accounted for the heat that is given to the system during the transition itself. And let's say we are talking about constant pressure process. Again, this could be a constant volume and you will just change it to corresponding thing. If you're talking about constant pressure process, then it will be the enthalpy change of the system, right? What is the heat given to a system at a constant pressure? That is H, right? Just recap, why did we get into enthalpy and internal energy? Q, delta Q, constant P is equal to delta H. Delta Q constant volume is equal to delta U, right? This is why H and U are so useful. Go ahead. Transition, TRANS. Yes, sorry, my writing is terrible. I mean, a lot of the professors here come to Thermo with pre-prepared PowerPoints. I could do that and my writing would look beautiful and my notes would look elegant, but you guys would hate it. Thermo is hard enough. The number one thing that will happen is I will be covering 2 times the material. You know how that will feel, right? You're like, whoa. I mean, at this point, I would be talking, I don't know, quantum mechanics. It slows me down and it's more engaging, but that comes at the cost of my elephant type handwriting. I cannot help it, sorry. So Q is equal to delta transition H. If it was a constant volume process, it would be delta transition U. Okay, but we are talking about constant pressure. So in equation, this was equation 3. Equation 3, we need to add delta S transition. Delta S transition will be the Q transition. So this should also have a transition, the heat given during the transition, during the change itself. That will be Q transition divided by the temperature of transition. And that will be delta transition H, the enthalpy change at that transition temperature divided by the transition temperature. So needs to be added. This needs to be added to equation 3. So I'm not going to write the full thing, but let's say you have solid going to liquid. Let's keep the gas part, it's the same idea, right? So then, and if this is happening at a temperature TF, then the S of the liquid at a temperature T will be related to the S of the solid at temperature 0 as 0 to TF Cp solid divided by, and you might not like that I have T inside the integral and outside the integral, so I can just call it T prime if you want to be rigorous mathematically, plus delta fusion H, the enthalpy change of fusion, and we talked about it, right? We can calculate enthalpy change of fusion because we know the enthalpy of the solid, we know the enthalpy of the liquid, is just a difference of those two, divided by the temperature of fusion plus T fusion till some temperature T, Cp liquid divided by temperature T prime, dt prime. And if you had more phases, you just have to add corresponding things. This is now correct. Now comes the second question for the ice cream part. What do we do about S of 0? Okay, Ryan, if you want your ice cream, this is your chance. This is like a game show. If Ryan doesn't get it in 10 seconds, the ice cream goes to whoever else. Countdown, 10. Huh, what? Are you guessing? Okay, it goes to JP. And you have to answer why also. It goes away from Ryan. Yes. There we go. Here's your ice cream. Okay, yeah. So at 0 temperature, the entropy is 0. And it's hard to understand this from our classical definition of entropy. It's easy to understand from the molecular description, right? Remember our molecular S of 0 Kelvin at 0 Kelvin is equal to 0, because molecular definition says S is equal to Kb, ln W. At 0 temperature, there is only one way of arranging anything. In quantum mechanics, that way is known as the ground state. The system goes to its ground state, it goes to the lowest energy level, and it just sits there. There are no thermal fluctuations, no motion is possible. It just sits in its boring ground state. 0 temperature is ground state. Here comes the more abstract part. How many people here have done any quantum mechanics? Some must have done it a little bit. Why should there be only one ground state? Why can't a system have two ground states? So, and think about chemistry, right? Why should a molecule in its ground state have only one unique electronic configuration? Why should there not be two possible? When we talk about oxygen, right? We know what is the 1s2, 2s2, whatever, right? We talk about one electronic configuration. We don't have two possible electronic configurations for oxygen in its ground state, right? That is a peculiarity of quantum mechanics, which you can show. But this directly boils down this fact that the entropy is 0 at 0 Kelvin. So when Karina, right? When Karina answered all this, she was, I think, thinking about quantum mechanical ground state being unique, right? She's nodding her head, so I'm sure she's right. You will study this in 482. Quantum mechanics says ground state is unique. And just to get a bit more abstract, I'm not going to write it in the notes. So quantum mechanics basically boils down to Schrodinger's equation. This is the x side, this is the inside. This is the wave function. And you calculate these wave functions, you get the eigenvalues, right? E0, E1. E0 is always smaller than E1. The other eigenvalues can be degenerate. And these other eigenvalues, everything corresponds to a wave function. For E0, there is always only one wave function, psi naught. There are no two wave functions, two ways of arranging the system, which will give you the same eigenvalue. This is a property of Schrodinger's equation. That's where this comes from. And this has a name, that the entropy goes to 0 at 0 Kelvin is known as our third law of thermodynamics. For any material, entropy is equal to 0 at 0 Kelvin. Any questions? So the third law is basically a direct consequence of Schrodinger's equation. Yeah, go ahead.
The interval we had before, right after S of 0, how do we evaluate that if it goes from 0?
What do you mean? This will be put at 0.
For the next
You need the value of the heat capacity.
T is 0. And so you actually
Oh, good question. Does anyone remember what we have talked about heat capacity versus temperature? For an ideal gas, how does it look like? It's a straight line. For a real gas, heat capacity goes to 0. So you have a 0 divided by 0 situation. When you have 0 divided by 0 in calculus, what is the name of the rule? L'Hospital rule, right? No, what is it called? L'Hospital. So you use L'Hospital rule in your equation. But you won't even have to do that. Both things just go to 0, and it will go to 0 because heat capacity goes to 0 as T goes to 0 in your equation number 4. And why? And in fact, this heat capacity goes to 0 as T cube. And if you take statistical mechanics next semester with Garrick Papoyan, you will study why it goes as T cube. That is something you need quantum mechanics to explain. Debye was able to explain it. Einstein actually got it wrong. Debye got it correct. So yeah, if heat capacity was constant, then you would have a problem. This thing would diverge, right? Everything would just blow up.
So you're saying CP proportional to 1 over T cubed, right?
Yeah, no. CP proportional to T cube. If CP was proportional to 1 over T cube, we would still have trouble. So in the numerator, actually, you don't even need L'Hospital rule. Let's just remove it because CP is going as T cube and the denominator is going as T. So life is cool. Okay. Wonderful. So everyone seems they're very They have mastered entropy? She has. She's confident. Okay, good. By the way, one of the things in this class is participation points. And for those of you who come here and ask questions, and I know there are many of you, there is Marco, there is Andrew, there is Karina, there is JP, and I know who you are. Even though if I don't know your name, I have your photos in the roster, I know who you are. So if you're coming to class and asking questions, that's you're perfect on your participation points. However, in the coming, there are many students, and this happens really around midterm. I get emails from students. I could not come to class on Wednesday, and I cannot come today, and I cannot come on Monday also. Can I come and take my midterm? You're making it really obvious that you don't bother to come to class. At one time, I can understand that is an excuse. 2 times, 3 times, really? Maybe you had a medical excuse and you pre-arranged it. So this is not exactly good. I'm posting videos online so you can go and refer back to it if something is not clear. But not so that you just start skipping class. It's not university policy, and I can be in trouble because I don't want to encourage. This is not an online university. Okay? We are not doing Khan Academy or Phoenix University of Arizona or something like that, right? So it's different. This is an engagement that's going on over here. So long story short, in the coming few lectures, there will be pop quizzes. There will be 3 pop quizzes over the remaining course of the semester. These pop quizzes are strictly participation only, in the sense that if you participate, you get full points. Okay, doesn't matter. But I want to keep a stack of who is coming. I want to keep a sense. So if I see a student did not show up in any of the 3 pop quizzes, then you won't get full participation points. Okay, if you miss 1 or even 2 of the 3 pop quizzes, then it's okay. I don't mind. I understand. But if you miss all 3 and you had not arranged with me a priori that you had a medical excuse allowed by the university, then is this fair? And you all are here, so you will say it's fair. I should ask the people, hey, hello, anyone on Zoom? No one's on Zoom. So because otherwise, I don't think it's good. And the material gets more complicated here on. It's important to come and participate. You cannot just go and good luck reading these. Okay, let's move on. I'm going to start a new topic. I'll just introduce it. I really invite you to go and read about it in Atkins, and whatever I'm starting here onwards, we will resume from here the next time. But this is really we are doing all of this so we can talk about equilibrium and chemical reactions, right? We want to study how much proportion will A and B form, whether A is going to B, whether B is going to C, and we have just set up the machinery for all that. So you're all basically now reaching the point where math is gonna kind of converge, and we will start doing useful things with it. You will look at phase diagrams of material. We will use this to explain, for example, why does ice skating work? How is it that you can ice skate? Anyone knows how does ice skating work? Go ahead. Wrong. Yeah. You are going the same answer? It's wrong. No, I will calculate in class for you that in order for that idea to work, you will have to weigh as much as an elephant, a big elephant, standing on shoes which are as tiny as a small guitar pick. The pressure is just enormous. That's not how it works. So I will prove to you using all this once we get there that ice skating does not work so that. In fact, it is still a bit of a mystery as to how ice skating works. The most accepted upon argument is that a nanofilm of water forms on the top of ice, and that's what you're skating on. And you can go and Google on this, and you will find articles in New York Times and Quantum Magazine and Wired still debating how does ice skating work. The melting explanation is wrong, and we will prove that in a few lectures from now on the basis of all this. That will require us to study phase diagrams first. Okay, but in order to do that, what we are going to do next is to talk about spontaneity. So we are going to keep talking about spontaneity, which we did. We already know that delta S total more than 0 is spontaneity. But now we will introduce the concept of free energies. Why will we introduce free energies? Because free energies, there is really no new information in free energies. This is just a way of doing bookkeeping about related to the entropy under specific conditions. So what do I mean by this? So we know that spontaneous change is delta S total more than 0, right? The problem with this one was that we always have to calculate delta S for the system and delta S for the surrounding, right? But we also derived an equation which allowed us to get away just with this system. What was that equation? It was an inequality starting with C. Clausius inequality, right? Clausius inequality said that if ds system is more than equal to the heat given to this system, then that is also spontaneous change, right? So this thing is nicer because we don't have to worry about the entropy change of the surrounding. We can just get away with the entropy change of the system. These two are equivalent. But there is still something not so nice about it. There is a Q hanging on the right side, right? We still have to worry about this ugly path function. And I don't want to deal with path functions. So free energies will allow us to, so this was not very nice, not very useful. This one was kind of useful, but it still has a delta Q, will allow us to express spontaneity conditions. And you have all seen spontaneity conditions in 271 or these other classes, but they come in a very rushed manner and it stays confusing. Here it's hopefully it will become very clear. Spontaneity conditions in terms of only state functions. And this will be very useful because we can just talk about state functions and get away with it, okay? However, this will not be very general. It will apply to processes at constant temperature and pressure or processes at constant temperature and volume, okay? It won't be, we won't be able to do it for very, very general conditions. These two conditions, however, are the typical conditions under which chemical reactions happen. So they are useful to us. In order to do this, we are going to introduce two new state functions. The first one is called Helmholtz free energy. Some books just call it Helmholtz energy. I'm going to call both of these things as Helmholtz free energy. And the second one is called Gibbs free energy. I will write down their definition. I will write down to you what is the thing that we are going to prove next time, and then I will stop. Helmholtz free energy is defined as U minus Ts. It's a state function, right? Because U is a state function, temperature is state variable, S is a state function. And Gibbs free energy is defined as enthalpy minus Ts. And what we are going to show next is that, what is the equation number? So let's call this as equation number 5. Let's call this as equation number 6. We will show that at constant temperature and pressure, the condition for spontaneous change is given by the Gibbs free energy decreasing. 0 means reversible. But now notice we have got rid of all path functions. It's purely state function, right? And at constant temperature and volume, the condition for spontaneous change is Helmholtz free energy. Change in Helmholtz free energy is 0 or negative. And the subscript I'm specifying because they indicate the condition under which a process is taking place. If a process is taking place at constant temperature and volume, you do not care about Gibbs free energy. You can calculate it, but it won't tell you much. If you're designing a battery, for example, and you want to study whether the battery will work or not, you have to look carefully whether the boundary in the battery is moving, constant pressure, allowing the thing to expand and come to constant pressure, or if it is a fixed boundary, it's a fixed membrane. If it's a fixed membrane, it's going to be constant volume, and you will be using constant Helmholtz energy. Notice something. So this equation number 7, both of them, 7a and 7b, are very useful because they are no path functions. Notice something happened. So far, we were talking about things increasing. Here we have things decreasing. So next time we will work through this. We will see, we will derive and see why they naturally arise.